Welcome back, everybody. Today we get to start 3.5, where we're going to be talking about, I'm just going to write EXP all caps, which is short for what? Not exponent, exponential, because they're different, right? And I know it's subtle. The difference is the variable. Okay. Exponential and log models. And look at that, we're in high fashion. All right. So I'm your coach. No? Okay. Is Coach a fancy brand? Coach is semi-fancy? Okay. So I'm Dolce. Armani, if you will. I don't know. I don't know a lot of fashion stuff. I buy Target clothes.
Me too.
I really do, but more often I just get them on Steep and Cheap. Or the Western store or Sam. Anyway, doesn't matter where I buy my clothes. Here we go. Turns out we have 5 different types of models. 5 models that we care about. Now, here's the deal. We probably could go more into all of these than I typically do, but I don't want to overload you with like the possibility. We'll look really briefly at them and we'll get some graphs up on the board just so we can see like, hey, what situation would this possibly be modeled with? But we're really only focusing on 2 nice models here. But I want you to know that the others exist. So for these, we're going to look at 2 of these, and we're only going to see 1 and 2, but I want you guys to tell me what's going on with these. So the orders aren't in any, like there's no particular order other than there's 5 separate models. Okay, so the first of these, I'm going to leave a blank here because we're going to name what it is, and we'll say it looks like this. Y equals AE to the BX, and the only requirement is that in this situation, B is greater than 0. Okay, what is going to happen with this graph if we have AE to the BX? It's increasing. And is it increasing in a nice linear fashion, in a quadratic fashion? Good. It's increasing or growing. This is the model for exponential growth. Okay, what sort of situation would we use for exponential growth, like real world problems? Money is a good one. Money, populations, maybe, but we'll talk about why maybe populations don't work for the whole thing. How old were you guys when COVID happened? 6th grade. Do you remember all the news? Did your parents watch a lot of the news during COVID? Do you remember watching a bunch of news about it? So if you do or don't, if you remember ever seeing the news, I bet you saw a graph that looked just like this. Why did they use that for COVID and disease in general, whether it's COVID or not? Yeah, like the more people that are infected, the faster it spreads to more people, and it just starts growing faster and faster and faster. Like that's an exponential model. Now, maybe it doesn't work for everything, but we have exponential growth. We'll use this one, and we will model with this one. Second one, we're going to write the same equation, AE to the BX, but this time we're going to require that B is less than 0. If A is less than, B is less than 0, instead of growth, what's this going to be? And what sort of situations would this make sense for? So what sort of things decay? Dark, but okay. We could expand on that. We won't. I rambled about it for like 20 minutes one day. Radiation's a big one. Unfortunately, money can also decay if you put it in the stock market and you're losing money year after year. That can happen. But we have exponential decay. All right, these next ones, we are not going to have any idea what they represent. And I'm just going to give us the names right now. And then we'll look at the graphs and see like, oh, what could we possibly use this for? Okay, so this one, Carl Gauss is a very, very famous mathematician. And here's how you spell his name, Gauss. So we get what is known as the Gaussian model. Now, his name shows up a lot of places, not as much as Euler's, but it does show up. So let's just see this, Gaussian model. G-A-U-S-S. Okay, the Gaussian model will look as follows. A-E to to the negative, and there's a fraction up here that's ugly, x minus b squared over c. And I'm trying to decide, do I really need, nope, here we go. And this is the nicer version of it that I'm about to show you, but I'll let everybody get that again. A to the negative x minus b squared over c. Now this one, and I'm going to add these other comments. Are you guys writing down what we use it for? You don't have to. Money, radiation, and whether or not you write it down is up to you, but I'm going to show you a picture of the Gaussian model. Here's a Gaussian model. Any idea, have you ever seen this picture in mathematics? Algebra 2 is where it would have happened, probably in the very end. So kind of. Did you guys do a bunch of statistics last year? In Algebra 2. Did you do anything called standard deviation? In Algebra 2 last year? Okay, what's standard deviation? Okay, so we're not doing a whole lesson on stats, just so you know. But if we had this, and I'm going to copy it so I can draw on it, and looking at this, Wisha, you're the one person that might have a good answer for this, just based on what we were talking about with some of your SAT stuff. Okay, if we have 100 people, do you think that it's reasonable that if, don't know why it does it every time, this would be the average? Now, whether it's 1 and -1 doesn't matter. Do you agree that most people should get the average if it's like really good data? And then there's a certain amount where the bulk of people will get scores in this range. Does that sound reasonable? So some people do a little bit better than the average, and some people do a little bit less than the average, but the bulk of people are here. Okay, and then you're going to have some people who do a little bit better, who are in this range, like a little bit higher above the average, and this range, a little bit lower. There's less people here, but it's like if my average is a 75, these are all my C's. And then here's a few B's, and here's a few D's. And then at the very other end, and this is with grades, there's a smaller region over here even, where people get A's. And there's less people that get A's and less people that get F's. This should happen, right? So this is called the normal distribution. That's what this is. More commonly, the bell curve, because it's shaped like a bell. This thing relates to statistics and standard deviations and all that good stuff. This is, if you take a big sample and you have some data that you're making sense of, this is what you hope to find, because it's really easy to make predictions if it's really done like this. When you guys, I don't know if you have any teachers that curve tests. So people never really curve it correctly, and that's okay. Like, it's good, because a true test, if I give it to, if there's 10 people in here, I would just put the mean right at the middle, and whatever the mean score was, I'd make that a C. And then I would do the calculation, say, oh, what's one standard deviation away from this? And then anybody who got above a certain mark would get a B. Anybody who got 2 deviations, which this distance is 1 standard deviation, anybody who got 2 would now get an A on the test. And realistically, it doesn't help most people. Like, it's not like, it can, but most real data is not like this. Usually what happens is it's either tilted like this and there's a hump there, or it's tilted like this and there's a hump over here. And if it's anything but perfect, if you fit it, if you curve the grade, a bunch of people are going to be made lower scores than they actually got. Like, it happens. We don't really curve when we say we're curving it. We just add points. And when I curve, quote unquote, my adding points is if we average a 71, and I don't really curve anymore because I give the retake stuff. But what I used to do is if the average was a 71, what do I want the average to be? Do you guys remember? 75 is what I want it to be. So everybody would get how many additional percent? That's how I curve it, just to make the average 75. Notice I don't do it the other way. If the average is 79 and I were consistent, everybody should get how many points taken off? I would take away 4% from everybody to give the C as the median value. Okay. Anyway, the Gaussian model exists. If we get into the stat stuff hardcore this year, we will see it. All right. Another one. Love it. This one's called logistic growth. Now, logistic can be kind of hidden, but what sort of model is this going to be? 100%. It's a log, right? That's logistic. So we get logistic growth. And lost my thought here. Okay, this one is much more realistic and realistic. Like it should have been the one that was used with COVID. It wasn't because it's not as scary looking and it doesn't sell as many commercials. That was teacher hat off, just so you know. You know what? I don't think it even has to come off. Do you guys think the media sometimes makes a bigger deal about stuff to get clicks? I assure you they do. I don't think that's controversial. If it is, I'm sorry. A over 1 plus BE to the negative RX. Okay. This model is much more realistic. And there's a ton of places that this one gets used. Here it is. Now, this model, if we look at just this part, do you agree it kind of looks like it's growing exponentially right here? Like it's going faster and faster. Okay, this is the model that should be used for most real world phenomena. So for example, population is a really, really common. So this one's stats. Stats is short for statistics. This is population. Now, just to kind of make it a little bit interesting, I hope, I don't know, would you guys tell me if I was rambling on and it wasn't interesting? Would you tell me? Can we just make a deal? You won't hurt my feelings because if I really want to say it, I'm going to say it whether you're interested or not. But if you're truly not interested, can you guys just give me like a really obnoxious, like show me with your face that you're not interested and or fries in the bag, something like that. Just, can it be boring? Boring. Sure. What's our code word? I mean, if everybody knows the code word, there's no real point to it. But okay. Holloway's a jerk. Oh, okay. I want here we go. I want a pop quiz. Okay. So, sure. Basil, what do you want? What's the code word? What are we using? Bedtime. Okay. Deal. So, check it out. Population. How many people are on our planet? We're probably closer to 9 billion at this point, but I don't know where. Okay, if we were to track the population and I'm just starting from some random point and I'm not even going to put years, population grew really slow at first. And then Black Death happened. It went down a little bit. And then influenza happened. AIDS happened. But notice it does this. Is it going to keep going forever? Do you think there's a point in maybe not your future, let's just say human future, where you're going to get to the point where there's 20 trillion people on planet Earth? We don't have the capacity because eventually we have more people than food, which means we'll get to, so it won't be the end of the planet. It'll be the end of reproduction for some people. Do you agree that eventually it's going to have to come over here to where we get some carrying capacity? Like we just can't physically support more people. But look at this model. This is the one that should be used. You can't get to a point where more and more people are infected by COVID because eventually everybody will have been infected and nobody else gets infected, right? Like there's a max number that it'll ever get to. It doesn't keep growing forever. It stops. That's the logistic model that we would use for that. Okay, the last one, whether it's natural or common, doesn't matter. We'll just look at log models. And log models, and I know it's different, logistic growth and just straight up log model. And the log model is just nicer. It's y equals, and I'm only going to look at one of them, a plus b natural log of x. And they look like this, a plus b ln x, and they all kind of look like this, a plus b ln x. Okay, these models, they're a little bit harder to put in like nicely. They don't start growing faster and faster. This one, harder to apply, but natural stuff. So earthquakes, tornadoes, those things are all this log scale. So that if you go up a magnitude of 1, you get however much 1 is over here times stronger. Cool. All right. As we're looking at these are the two that we really care about. And the cool part is we've already done some of it. Okay. Anybody dying to do these other models? Anybody living to do those other models? That's probably the better way to say it, right? All right, here we go. Let's do the first two models then. We're going to look at 1 and 2, and we're just doing word problems today. All right, so decision time. We could spend times writing paragraphs here. Or we can all just agree if we write the page and where the problem is, we don't all have to write paragraphs for our problems. Okay, so example, apply is what I'm going to call all of these. And the first example, I'll put it up on the board, but we are going to do the check mark problem, and they call it checkpoints. But I'm just going to say it's a checkpoint on page 240. It's on the very bottom. I'll put it up on the board. Okay, if you guys are crazy about your notes, leave space. It takes this much space. Okay, so I'm going to just copy and paste. I can zoom in a little bit, I suppose. And you are all going to get like a minute and a half prior to me. And I want you guys to help me come up with a way to get through this problem. So here we go. The number of bacteria in some culture follows the law of exponential growth. Fantastic. After 1 hour, we have that many bacteria. After 2 hours, we have that many bacteria. Cool. I'm going to give you guys, once I get this posted or pasted, weird. Here's problem A, and I'm just going to put it right here. You guys get about 60 seconds talking with one another. Don't care if it's a good approach or a bad approach, but I want an approach. And this is page 240, I'm sorry. Page 240. I'm going to pause the video. You guys are going to help me try to set this up. Which one is exponential growth? What does it look like? Y equals AE to the power of BX. Everybody agree with this? Okay. Now, just as a kind of reminder, because I heard you guys talking about it, somebody was saying A is something, and I'd like to know, how are you getting that? What does A represent, number 9? What's up? What do you say it, and if it's wrong, we'll sort it out. It's okay. Okay, can anybody help? So it won't be time here. If it were P, what would it represent? And what's principal? The start. So good. Leigh says start. I'm going to say initial, but I'm okay with that. That's my initial amount. Every time, that's going to be my initial amount. Because if x is 0, and that's like at time 0, then this whole thing is just 1, and it makes sense. So that's how many we started with. Okay, what is this? What's the A in PERT? Because it's the same formula. If I write this, because do you guys see it's the same formula, and do you agree it's the same formula? Okay, what's P is principal, my initial amount. What does this represent? The account balance. So do you agree that that's like saying the final amount? And now I'm going to be more specific. At which time? And which thing over here is time? I know it's weird because it's not the right letter here. This is my time. So this is my final amount at this time. Okay, so this is the equation that we use. Now, for this, I'm going to help make this a little bit more mathy, which I hope is a helpful thing. Like, it might sound scary, but when I read this problem, there's context to it for sure. But do you agree that all we're looking for is something that follows this model, and then it passes through a couple of points? I know that after 1 hour or a 1 hour time, there's how many bacteria? There's 100 of them. And any other points that I know that they just kind of hide? At 2 hours, there's how many? 200. Okay, we have this information. At this point in time, we're trying to predict at 3, right? Now, I might actually change the letters, and it doesn't matter if we change the letters or not. Instead of Y, I would probably call this P for population, is what I would do. And instead of X, I would call it T for time. But it's the exact same equation. We'll just keep it like this. Now, here's a weird part. If we want to be able to predict at 3 hours, I need to know the initial amount for sure, but I also need this B value. Do you guys agree with that? So I'm just going to make that note here, and I'll do it in yellow. That's fine. We need 2 things, and 2 things only. We need A, and what was the other one? B. Now, That's our whole goal. That's it. If we can find A and B, we're good. The good news is that my equation, the way I've written it, I have X and a Y. Is there anywhere that I know an X and a Y that I can plug in? Yeah, sure. It doesn't really matter which point we pick. Let's pick this one. So using, and we're going to split this up. I'm going to do two different colors, but for a very specific reason. Using the point 1, 100. What I want us to do is let's solve this thing for, I don't know, whatever we want to. Let's solve it for, and you guys will help me decide. Solve for, and we're going to leave it blank for now, but there's going to be a letter here. Okay, let's just try. What is the population after in this first data? I have a population of 100 when it's A e to the B times what? Whoops, 1. Okay, I want to highlight here. Here's my 100, my Y value. Here's my 1, my time. Now, we have some options. I didn't tell us what we're solving it for, but is there anything that we very clearly could solve for? We could solve for A or B, realistically. Which one's easier? Louder, whoever said it. A, because it's one step away. Do you guys agree with that? So I'm going to solve for A initially. Okay, now this is going to be irritating because we're going to see an issue with it. But I think I get A equals 100 over e to the b. Now, this is not a number yet. Why? Gosh, I have two unknowns, but I'm going to put a star next to this for a second. Do you guys, and I'm going to write this out. It is entirely up to you if you want to. Right now, what we have is A in terms of, what variable do we have it in terms of? B. When you see this statement, something in terms of something, all it means is here's an expression written with another variable. Okay, now we have a little more to do, and I heard Krina say it. What was that word that you said a moment ago? Substitution. Do we have another point? Let's use the other point. Use other point, and we just found a value for A, right? Kind of. And we'll say value. I'm going to put quotations around it because it's not really a value of A. So let's try this again. If we do the exact same process, what's my final amount for our second data point? So we get 200 equals, now I could write an A, right? And maybe I can if you want me to, but instead of A, what could I possibly write? 100 over e to the b, okay, times e to the 2b. Do we all agree with this expression? Now, with the color coding, I hope it's really clear, but if it's not and you're not using colors, that's okay. I would make sure that you very, very clearly make it clear that that's where we plugged it in. Okay. How many variables are in that new equation that we just had? There's only one. Okay, I'm going to give you guys a little time. I'm going to give you a head start. Talk with each other if you need to. Can we solve a single variable with a single equation? Find me B. Solve for B is your job now. Dot, dot, dot. Anybody else struggling with this? Okay, you don't need to. I'm going to rewrite this, and I'm not doing anything other than rewriting it. Do you agree that this is the same thing, and I'm just going to do all blue now? Is this the same expression? Are those equivalent? Yeah, why would I possibly write it like this? Basil, you were able to tell me it with the other number. Why did I do this? The exponents just subtract. Right? If I have something to power over the same thing to a different power, these just subtract, which means my very next line, I get 200 equals 100 e to the, what's 2b minus b? b. Okay, and I'll just make a little note here on the side so we can do this. A to the x over a to the y equals a to the x minus y. That's a property that I just used. Can we solve it for b now? How? So divide by 100, and I know it's going to be 2, equals e to the b. There's one more little tiny bit to do here. Take the natural log of both sides, and I get b is exactly equal to the natural log of 2. And somebody's going to hook it up approximately 0. I don't know what it'll be. 6. Let's go 4 digits here. 6931. Okay. So what we just found in this population is 69%. Like that's the growth rate, 69% per hour seemingly. And it's going to keep stacking like this. Okay. Question, Addison. From like here to here? All I did was I just took the natural log of this, the natural log of this, and those canceled. So natural log is the inverse of base e. So when I do this, if you want to use the fancy property, the b goes out front. And I'll go ahead and do that. We have the natural log of 2 equals b ln of e, and that's 1. Yep. Okay, so I'm going to put a star next to this one also. We now have an exact number for b, right? Well, a moment ago, we had solved for a, but we didn't get a number, right? We had an expression in terms of b. Now, get a using that value of b. And we have to make a decision. Are we going to use b as the natural log of 2, or are we going to use b as approximately 0.6931? Lay says use a natural log of 2, and I agree with you. Okay. Now, she didn't really say that, and you guys might go, why on earth would we do that? One, it is a little bit more accurate, but there's something else awesome. If I plug this in, e to the ln 2, what's e to the natural log of 2? Good. That's the inverse, right? 100 over 2, which says what was a? Okay, what did we just find? Okay, so there were initially 50 bacteria put in this petri dish. Cool. Do we have, if we look at our model, and I'm going to scroll up here real quick, do I have A? Do I have B? And I'm trying to find it when time is 3, right? So I have X as well. Well, let's just plug it in. If I want to know the population Y, if I start with 50 and I have e to the here, if I was typing into my calculator, it is up to you. I don't mind using ln2 if I'm using my calculator, times how much time? 3. And could I write the 3 right here? Like that's bx still, right? Just randomly, not really random. Could I write it here if I'd rather? Could I have written it right here? Why would I have done that? Why do I like this more than times 3 on the other side? Okay, so if you don't see it, that's okay. But tell me, if I have this written, 3 ln 2, is it clear that this is ln of 2 cubed? If I write ln of 2 times 3, is it as clear? No, I can do this whole problem without ever touching my calculator. Is it okay if you touch your calculator? Yeah, but if we use this, it's a little bit easier. I think this comes out to be, and I'm not going to touch a calculator. This is 50 e to the ln of, I'm going to say 3 ln 2, or ln of 8, if you will. I'll do that. And what happens with this? It'll be what? 8. And what's 50 times 8? Boom. Because we used e to the ln 8. And you can confirm on your calculator. I just didn't want to have to grab a calculator here. But because I know e to the ln of whatever is always going to just cancel out because these are inverses, just like we did down here, it's going to keep working. We're just using that inverse property. And to be very, very clear, because I think I can say that and somebody will be like, oh yeah, okay. Like you might not recognize it still. We have natural log of e to the x equals x. Here's one property where they just cross out. And then the other one is e to the ln x, which again, ln and e, they're inverses, so they just cross out and it leaves me with x. These are my two properties for inverses. And I'm just using that because I had ln2, so I can calculate it without a calculator. Okay, was there a context to this problem? We need a sentence, and it can't say it. It has to be very clear. Help me write a sentence here. What are we modeling? What do we just find? What about the bacteria? The population of bacteria. Depends on the grader. You can say pop for me. I'm fine with it. The population of bacteria after 3 hours. Was it hours? I didn't read the problem that closely. Okay. Is 400. Now, one of the cool things that we have here is a really easy way to predict stuff. If I wanted to predict after 200 hours, would it really make a whole lot of sense, do you think? I don't know. It depends on the bacteria, right? If the petri dish is only this big, I probably can't have it keep growing consecutively for 200 hours. If I have a gigantic petri dish, then maybe. Like, just depends on how much available land and resource there are. All right. Doable? Okay. So, we have a decision to make. Are we going to have a homework split? You know what? I'm going to give you the whole assignment right now. And I'll tell you right, it's going to be due Wednesday. Okay. If you want to start any, we only did like one of them so far. So let me put it all up here. And I don't think that this will change. Holy emails. Did you guys buy a bunch of Black Friday stuff?
No.
Yeah, me neither.
Do you buy more chessboards?
What?
No.
So the chessboards aren't for me, just so you know. It's so that if we wanted to have a chess club and chess tournaments and stuff, we could. It's not just me being crazy and collecting chessboards. All right. So this is lesson 3.5.1. And I'll put the name and stuff. Homework 3.5. This will be due Wednesday. If there's a population problem, you are able to tackle it at this point. You will find this on page 245. And I want you to do problems. Really? That doesn't look right. 1. But wait. You're welcome. You'll give me more things. 1. 5 and 6. Sorry, I'm trying to tweak it from what we had before. You said you guys like money? 15. 27. There's going to be one more in here. I just got to find it. What's more interesting? A website growing, a population growing, bacteria growing? Population. Tallahassee? All right. Indeed. 32. Cool. Okay. Here's the crazy thing. And travelers, we got to talk. Did I give your sheets back?
No.
I'll do it right now. This is the last section.
Oh, no. No.
And we're going to finish the last section tomorrow.